Hello, everyone. I would like to discuss section 10.5, the solid state of matter. So if you think about this module, we started out by talking about the forces that might lead to things sticking together. Then we talked about the liquid state. Then we talked about phase changes, and then we're ending with the solid state. So the learning objectives here: define and describe the bonding and properties of ionic, molecular, metallic, and covalent network crystalline solids. Describe the main types of crystalline solids: ionic solids, metallic solids, covalent network solids, and molecular solids. And then we won't really be too concerned with the last learning objective that we're showing there. So when we have a solid state, most of the time we will have something called a crystalline solid. In a crystalline solid, we have a regular repeating arrangement of the molecules, atoms, or ions that make up that solid. Sometimes it's possible to get a non-crystalline solid. We would call it an amorphous solid. Things like a glass are examples of amorphous solids. And we're showing a picture here showing kind of the distinction between crystalline and amorphous. And basically the idea is, think of amorphous as just not quite as organized as crystalline. And if you want an amorphous solid, generally what you want is you want to cool it down really quickly so it doesn't have time to get into the best arrangement that we have for a crystalline solid. We'll mostly be focusing here on crystalline solids, but just be aware that there are also amorphous solids. So we will often have these regular repeating patterns, and there's another section that goes into more detail on that, which is something that someone might choose to do for a presentation. So let's talk about the different possibilities. And some of these we've already discussed, so we'll go and talk about them, but it's not necessarily new. So with an ionic solid, we have some arrangement of opposite charges, so positive and negative charges. We're showing here a diagram of a sodium chloride ionic solid, and you can see this repeating pattern of purple and green, purple and green, purple and green. And the idea there is you have a positive charge surrounded by negative charges, and negative charges surrounded by positive charges. So that's the arrangement that they will typically have. Ionic solids will tend to have very strong forces holding them together. These are actually chemical bonds, right? You have full positive and full negative charges that are attracted. That's very difficult to break. And so we have very high, typically very high melting points for ionic solids for that reason. This one we haven't talked about yet, metallic solids. So we know that most metals are solid just by looking at the periodic table. And there are some exceptions, of course, but most of them tend to be solids. However, they also have this property that you can easily change their shape. And it's not because they're necessarily about to melt and form a liquid. There's something else going on there. And what's going on is something called metallic bonding. And the way we visualize what's going on here is, if you think of the metals tend to want to lose electrons. When they lose those electrons are just going to kind of go out and not go anywhere because no one else wants them, right? So all of them are trying to lose electrons at the same time. So what ends up happening is you have all of these positive charges of the core electrons and nuclei of the metal atoms, or metal ions essentially, and then that is surrounded by what we call a sea of electrons. And these are what we call delocalized electrons. They're not necessarily on a particular metal atom. They're just all around, and they're holding all of those metal ions together. So this is a very strong attraction between those essentially metal ions. So they will tend to have higher melting points. However, their property of being able, where you can easily shape them, is also because of this, because you can move those metal ions relative to each other fairly easily because the bond is what we call delocalized. It's sort of, again, the sea of electrons holding them together. So it's very easy to change the shape of metals without breaking them because of this kind of bonding. Covalent network solids are essentially things held together by a large series of covalent bonds. So things like sand are held together by covalent bonds. And so it's just this big network of covalent bonding. Diamonds would be another example of this. So again, very strong attraction here. These would have very, very high melting points, but they're also very brittle. They do not easily shape the way metals do because you have to break the bonds. The bonds are not delocalized. They are specifically between atoms, as we're showing in these figures here. And then we have molecular solids. So molecular solids are molecules that are held together by intermolecular forces. So we discussed the intermolecular forces in the first section of this module. They tend to be fairly weak compared to many of these other things. Many molecules will tend to be liquids or gases at regular room temperatures. So we have to get to often very low temperatures for these molecules to become solids. Some of them that are solids are because they have very high melting points. So things like sugar, for example, has a very high, I should say they have very high molar masses. So things that, of course, they have high melting points if they're higher melting points if they're solids. But things that have higher molar masses like sugar will tend to be solids for that reason, just because of their molar mass. Iodine, another example of something with a high molar mass, and therefore is a solid. So we have molecular solids. So crystalline solids have properties, and they can vary between the different types. And we've talked about some of that here already, but this table summarizes that. So ionic and covalent solids will tend to be very brittle because they are somewhat localized in the bonding, whereas metallic solids will tend to be easily shaped. So we say they're malleable for that reason. Metallic, ionic, and covalent all have very high melting points, whereas molecular solids will have typically low melting points. The table is also showing the kinds of attractions that are present and the types of particles that are held together. One thing I should also mention, in this book we're throwing molecular also would include atoms. So if you have, for example, the noble gases somehow are solids, you would have a very low temperature for that to happen. But it's possible, and we would categorize that as a molecular solid because it's the same type of attraction that molecules would have. So just be aware of these different types of bonding, what types of particles have the types of bonding and the properties associated with those types of bonding. So there's some interesting things about future materials here I'm not going to get into, but I think they are very interesting, so I'd recommend looking at that. And then we're not going to really talk about crystal defects in this class, but something that is also a very interesting topic. So feel free to read those if you would like to. However, we are basically concluding Module 10 here. So go ahead and get ready for the quiz based on the materials for this module.